Good morning, students. Audio video is okay.
Yes, sir.
Yes, sir.
So, welcome in next lecture of Math F242 Operation Research. So, in last class, we have completed or we have revised the basic of probability theory. Now, we will start the actual course. Right, means that previous was also the part of the course. We will ask the question from there also, right? But here now onward we will study the application of optimization operation research or the probability theory. So very first chapter is the queuing system. So here we have this system. So what you are noticing here, anyone, in all the pictures, what you are noticing?
Sir, there are many queues.
They are the congestion queues, right?
Yes.
People are waiting. Here even you can notice that data is waiting for the processing. In one figure you can note that data is also waiting for the processor, meaning communication call is waiting. Overall there is a congestion of the people, congestion of the data, congestion of the communication call, right? Here we have seen we have the different situation. So in this chapter we will study the queuing system in detail, right? Means how to do the mathematical modeling, right? Mathematical modeling of this type of the situation where we face the congestion, where we have to wait, where we have to make the line. So this is from the EDT notes chapter 7. So this theory was developed to provide the models to predict the behavior of the system. In the system always we have the customer and the server. So how they are behaving in the system or in the queuing system. So that attempt to provide the service for randomly arising demand. So means randomly arising demand means customer are unpredictable in nature. So he can arise, he can give the demand, right, at any moment. So to deal this type of the things, we have the mathematical theory known as the queuing theory. And it is not much old science. It was developed in 1909, right, by the AK Erlang. Actually, he was in the telecommunication department, and there from there he published one paper, right, theory of probabilities and the telephone conversation. Means there he presented the mathematical model for the communication call. And after that we have the lot of application of the queuing theory. Means you can see we have the waiting, we have the congestion everywhere, in the grocery shop and at the front of the ATM, right? In the reservation counter, means in the even in the over the computer when you make the big program in the Python or MATLAB. So it a lot of commands are waiting, right? So lot of commands are making the queue there for the processing. So everywhere you can face the queuing or congestion or the waiting. So here we have the right scientific study of the congestion. So the basic phenomena of the queuing arises wherever the shared facility needs to be accessed for service by the large number of customers. Means this is the condition. This is the condition, right? Means if question arises, why we have to make the queue? Why there is a congestion? So whenever the available service facility is not able to give the service at the particular point of time to all arising demand, right, to all customers, then the means the systematic way to get the service will be to make the queue, right? The systematic way, the or the disciplinary way to get the service will be the just you make the queue, right? Whenever the current service facility is not able to provide the service at the particular point of time. So queue or waiting line is formed when the service facility is not able to cope with the number of customers desiring service at that point of time. Means in general, at the particular time we have the more customers than the available service facility, then those customer make the queue, right? So this is the disciplined way to get the service. Now, queuing theory discuss the large number of mathematical model to describe the different waiting time situation. So, in this chapter, we will study the different condition with different architecture of the system, right? Where we have to make the queue, right? So, in general, if you want to provide the service, very important line I'm telling you. In general, when you have to provide the service to all the customer, the service facility must be more than the service facility must be or average service facility must be more than the average arrival of the customer. Average arrival of the customer. So here the average capacity of the service facility should be more than the average number of arrivals at the service station. Otherwise, if it is not so, if we have the more average number of customers, then there is the flood of the customers, right? There is the havoc situation, there is the infinite queue, never you can satisfy all the customers, right? Never you can satisfy all the customers if the average rate of the arrival is more than the average service facility, right? Then you cannot provide the service to all. So I am telling you that it is the necessary condition to solve the queuing problem or congestion problem, that average capacity of the average capacity of the service facility must be more than the average number of the arrival. Now the question arises: if the service facility is right, if the service facility is more than the arrival, then why there is a queue? Anyone can predict? Anyone can answer? If I'm saying that it is the necessary condition to solve the congestion, that the capacity of the service facility must be more than the average number of the arrival, then there should not be the queue.
But still,
So
sir,
why there is a queue?
the number of
Pardon?
customers arriving can be greater than average.
Pardon again?
Sir, the number of customers arriving in a time period can be greater than the average number of
Yes,
customers.
because the customer is unpredictable in nature, right? Because the customer is unpredictable in nature. When and how many customers can come, we have the idioms na, ग्राहक और मौत का कोई समय नहीं होता, right? Both can come at any moment. So we are talking only for the point of time. At the particular point of time, we may have more customers than the available service facility, right? So at that point of time, they will form the queue, right? They will wait, and because the average service facility is greater than the average arrival facility, so all will get the services after waiting some time. So customers are unpredictable in nature. So now, if there is the queue, what you have to do? So management is often, right, faced with the problem of deciding the proper amount of the service capacity. Means now, if you are the decision maker, right, if you are the service provider, or if you are the service facilitator, then you have to decide what the, right, then you have to take the decision, then you have to decide, right, what, how you should provide the service. If there is a queue, for example, if there is a regular queue in front of the ATM, then bank has to decide to install the new ATM. If you are at the reservation, there is a long queue, long waiting queue, right? So to means to set up the new reservation counter, we have to keep one additional serviceman in the shop. So always, are you facing the lagging?
Sir, it was earlier, now it's fine.
So So you have to manage. You have to manage the for managing the queue. For managing the queue, you have to adjust the service facility. So what you can do? Anyone can answer, please. What you can do as a decision maker? If there is a queue, what you can do? Simple answer. To
So maybe
minimize
add
the
another
queue, yes,
add another
you
service
can
facility.
increase the service facility, right? You can increase the service facility. So here, to avoid the waiting, increase the service facility, increase the. So when we are increasing the service facility, when we are adding the additional serviceman, so he will take some wages, increase the service cost. When you are installing the new ATM, it means you are adding the new technology, again adding of the service cost, right? So when we increase the service facility, what will happen? When we increase the service facility, what will happen? The service cost will increase, right? The service cost will increase here. So to avoid the service cost increasing the service cost, what you can do? To avoid the increase in service cost, then what you can do? Simple, don't increase the service facility. So what is the demerit in that? Simple, don't increase the service facility. Then what is the demerit in that?
Increasing length of the queue.
Yes, there is an increase in length of the queue. Means less service facility cause the long waiting line. That is the loss of the customer. For example, when you have to wait a more at any line. So generally, what is the what we you face? You face the impatience. You generally try to leave the line as early as possible, right? So you have the face impatience, right? Means you try to go elsewhere. That is the loss of the customer. When there is a loss of the customer, it means loss of the revenue. If customer is not coming to you, then that is the loss of the revenue. For example, in one tapri, you are not getting your tea or your samosa at the proper time. So what you do? You change your tapri, right? So that is what? That is the loss of the customer. Ultimately, loss of the revenue, right? Even loss of the goodwill of the shop. यार ये ठेली वाला तो अच्छा नहीं है. That is the loss of the goodwill. Social cost, right? Now another important is you customer, we have to pay for the ideal employee also. We have to pay for the ideal employees also, right? And the cost of the lost production. If we have the less manufacturing facility, then we have the loss of the means lost we have the lost customer production also. So everywhere we are facing the, right, everywhere we are facing the loss of the. Hello, hello,
Yes,
Yes,
sir,
sir,
you
you
are
are
audible.
audible.
is there any time lag?
So there was, now it's fine.
Just wait, I'm changing the network. So now audio is okay. So I was
Yes, sir.
talking, if we who is some doubt.
No, sir,
So
you just confirm.
I was talking I was talking, if we have the more facility, we have the more service cost. If we have the less service facility, then there is the more waiting cost. Means when we are so here means that is the decrease in the service cost. When we have the decrease in the service cost, but it increase the waiting cost, right? But it increase the waiting cost. So what we have to do here? What we have to do? Now the optimization arises. We have to optimize the service facility so that we can we can manage the service cost and waiting cost optimally. It means what we have to do, we have to adjust the service facility in such a way that total cost should be the minimum. Total cost should be the minimum. Total cost of Total cost means the sum of service cost and the waiting cost. Service cost and the waiting cost. So that we do in this chapter. So we have to make the balance between the cost. Minimize the expected value of the total cost per unit time. We have to manage the total cost per unit time. Right? So that we have discussed. So means if the service level here we have the service level, right? Service level to maintain. If you increase the service level, then the cost of the service increase and cost of the waiting decrease. So we have to make the balance between the total cost, right? So we have to make now in general when we have to make the balance between the cost and the value. Value means customer value, server value, and all these things. So from here we can understand the definition of the queuing system as, right, customer needing the service are generated over the time from the population of the prospective customer. I will explain this definition, right? But this is the scientific definition of the queuing system. Population of the prospective customer. So you from here you can note that this is the one important word. The customers thus generated arrive for service according to some pattern. Means when the customers are arising, so it follow the some pattern. On arrival, when there is a queue, if the server is not idle, so on arrival customer is given service if the service facility is idle. If the service facility is busy, he joins the queue. He joins the queue if service facility is busy. At some time after arrival, customer is chosen from the queue for providing the service by some service discipline. So from now there is a queue. Now there is a queue whom you have to give the service, that you have to decide, right? So we have to follow the some service discipline or say queue discipline. The customer is given the service by the service mechanism. After the service is completed, the customer leave the service station. So that is the situation of the complete queuing system. So now we will study all these technical terms one by one. So here we have the situation, right? So here you can say that we have the population, right? Here we have the population, and population are, right, means from the population some wants the service, so it is generated and they join the system. And if the server is busy, they will form the queue, and following some queue discipline, the customer get the service from the server. and after getting the service, he will be the served customer and he leave the system. So here we have the right population of the prospective customer. From there, the customer arrive, right, and enter in the system to form the queue. And then after, in the from the service facility, the customer get the service, and after that he become the served customer. So from here we can judge these are the some basic element for defining the queuing system, right? So here first one is the population of the prospective customer, then arrival pattern. You have to write like this only. If I ask, right, what are the basic element of the queuing system, then you have to write this only, the probability distribution of the inter arrival time. No other word you can use here, right? Then queue discipline or service discipline, service mechanism, probability distribution of the customer service time, and state of the system. So now let us study all the element one by one. What are these? These are the basic element for defining the queuing system, right, one by one. So here population of the prospective customer means, for example, we have the population for drawing a money from the ATM. We have the population, right, for purchasing the item from the shop, from the grocery shop. We have the population for for seeking the reservation, right, from the reservation counter. From there means means we all are the population, right? So now from there the customers are generated. So here this is an input source. This is an input source from which customers requiring service are generated over the time, right? This is the input source from where the customers can be generated to seek the services, right? To take the services are generated over the time. Now this population can be the infinite and population can be the finite. For example, here anyone can take the money from the ATM. So here you can say that population is infinite, or population is not infinite, but you can say that the from those who have the ATM card can draw the money from the that ATM, right? Can draw the ATM. So that may be the finite but large number, right? But for example, the bathing in the Ganga Nadi, right? Ganga River, bathing in the Ganga River. So what is that? We have the infinite population, means anyone can bath at any place, whether in Hardwar, whether in the Varanasi, or whether in the Kolkata, anywhere any person can bath, right? So that type of the situation come under the infinite population, right? But for example, we have the factory. In the factory we have the 10 machines only or 20 machines only. So if the machines are getting the breakdown, right, are getting the breakdown, then we have to repair those machines only. So in that case the population is finite. Population is finite. So population can be infinite, population can be the finite. If it is a finite, we denote it by the K. If we denote it by the K, so in actual practice, the finite population which is so large that arrival rate is unaffected. When we say the population is infinite, when the arrival rate is unaffected by the number of customer in the system, are assumed to be a infinite. When there is no effect, no impact of the population size on the arrival pattern, then we say the population size is infinite. Otherwise we say the population size is finite, and we denote it by the K. Then after, now we have the population. From the population customers are arriving, right, over the time. So how the customers are generating? Customer may come at any moment. Customer may come at any moment, right? Customer may come at any moment. over the time. So how these are generating, how these customers are generating. So means probability. So because it is a random, customers are unpredictable in nature, right? So the random means the generation of customers are totally unpredictable in nature. So here, if you say the inter-arrival time, right? This is what? This is the random variable, and you know that random variables are characterized by the probability distribution. So now next, the probability distribution of inter-arrival time. Inter-arrival time. So here means it follows some statistical pattern. It follows some standard or non-standard, but some statistical pattern, right? So the statistical pattern by which customers are generated over the time must also be specified. The time between the consecutive arrival of the customer is called the inter-arrival time. The time between the two consecutive arrival are known as the inter-arrival time, and it is the, you can say, inter-arrival time, and it is nothing, it is the continuous random variable. So you have to define its PDF or the CDF. Inter-arrival time is characterized, because it is a random variable, it is characterized by the either the probability density function or the cumulative distribution function. So in general, it is seen that different inter-arrival times are not the same. In case the inter-arrival time is the random variable, it will be assumed that they are independent random variable. Naturally, when the past customers have joined, or when the future customer will join, right? It is immaterial to me. So all the inter-arrival times are independent to each other, having the certain probability distribution. So here we have to define the inter-arrival times by the particular distribution. It may be approximated by collecting the data for the large number of the arrival of the customer. Means that statistical pattern, that distribution, we can determine whether it follow the exponential distribution, whether it follow the normal distribution or the gamma distribution, or arbitrary any distribution that you can judge with the collection of the data. So here we have the different situation. Customers are arriving at the different points. So this is the different arrival patterns at the particular, right, time interval. You can notice how the customers are arriving. So we assume that the on an average this much customers are arriving, that is the arrival rate, and we denote it by the lambda. Mean time between the arrival would be reciprocal of the lambda. Means here the 1 upon lambda denote the mean time. Mean time means expected or average of the inter-arrival time, right? It is the average of the inter-arrival time, and it is reciprocal of the lambda. It means, for example, suppose mean arrival rate is 5 customer per minute, right? If it is given to you 5 customer per minute, it means mean time between the arrival will be the 0.2, means 1 upon 5. So at that time, 1 upon lambda, that is the mean time. In general, we denote it by the beta. It will become the 1 upon 5, that is the 0.2 minutes, right? 0.2 minutes. So that is the average time. Now, suppose the FT is the PDF of the inter-arrival time. So I have told you, if the inter-arrival time is the random variable, then it is characterized by the PDF FT. So if FT is the PDF, what is his expectation? If I want to find the expectation of the inter-arrival time, ET, so what is the basic formula? Because T is the continuous random variable, so integration value into probability, T into FT into DT. That is the mean arrival time. And mean arrival time is what? Mean arrival time is what? We denote it by the 1 upon lambda. So in this case, we have then the mean time between the arrival is, right, 1 upon lambda integral 0 to infinity t into ft dt. It is visible. I think in PPT there is no eraser. 1 minute, I have to try. Right, so here we have the 1 upon lambda is equal to integral 0 to infinity t ft dt. So mean arrival rate lambda will become, right, lambda will become 1 upon integral 0 to infinity t ft dt, right. So in this way we can characterize the intervariable time with the suitable probability density function. Now from the population, customers are generated, right. So when the customers are generated and service facility is not able to provide the service to all customer at the particular point of time, so they will make the queue, right. So customers are making the queue here. So here we have the queue. Queue is characterized by the maximum permissible number of the customer that it can contain. Means for example we have the means dispensary, right, clinic. There we have only the 15 waiting chair. So at most 15 patients can be accommodated there, can wait there. If we have the more customers, then they have to go to elsewhere, right. If we have the more customers, then they have to go to elsewhere. So whatever the permissible limit, right, permissible limit of the customers, that much can be, that much can wait in the particular system. So here the queue we define by the system capacity. So here Q is called the infinite or finite. So Q can be the infinite or finite if the number of this number, this capacity, this limit is finite or infinite. The finite Q will be specified by specifying the maximum number of the customer that is the queuing system can hold. For example, whatever the example I have taken for the clinic, there I have told you we have the 15 waiting chair. It means the capacity, system capacity is equal to 15, right. So we denote that system capacity by the small m and it is equal to 15. So in the small, so this number will be denoted by the small m. In this small m denote the number of customers, in service, number of customers in service, with service facility plus number of customers, in waiting, number of customers in waiting. So the system, when we call the system capacity, it means we are talking the number of customer in service plus number of customer in waiting. So this m can be finite, can be infinite, depending over the situation. Now in the case when the system has m customers, the maximum admissible number, then the arrival customer at this instant will not enter the system and is lost as a customer. Means if our capacity, is full, there are 15 patients in the clinic. If 16th is coming, So that 16th patient is the lost patient. He has to go elsewhere for the services, right? For the diagnosing, for the inspection, he has to go somewhere else. So that is the loss of the revenue, loss of the customer. So that we have to optimize how much capacity we should keep, right? Means what should be the value of the M. But if you take the bigger area, then you have to pay the more rent, right? So according, you have to optimize that M also. Means again, this is the optimization of the service facility. So you have to optimize the service facility according to your need. Then after we have the queue discipline or the service discipline. Now we assume we have the long queue, right? Now whom you will give the service? In general, what is your thought to provide the service? If there is a queue, you are you are the service facility. Whom you will select? Whom you will give the service? First one. One answer is first one. Always. If you are the doctor और कोई मर रहा हो तो क्लिनिक में बहुत सारे वेट कर रहे हो और कोई मर रहा हो तो, if there is any serious one. Second answer is high priority. Third is one in need. For example, if we have the situation, you have the godown, right? और तुमने सामान भर दिया, और भरने के बाद जो पहला सामान भरा वहां पे, जैसे किताबें एक के ऊपर एक रख दी तुमने, तो अब सबसे पहले कौन सी किताब उठाओगे? जो सबसे पहले रख दी वो कैसे उठाओगे? In that case also the priority will not work. कि बीच में से कुछ खींच ली, जो आज मैथमेटिक्स पढ़ना है तो मैथमेटिक्स की किताब निकाल ली. So what are those situations? Yes, means queue discipline depend on the condition. So we have the many discipline, right? Method of selecting the customer. Queue discipline or service discipline means is the method of selection of the customers from the queue for service is called the queue discipline. How you are selecting the customer from the queue, right? Usually the customers are serviced on the basis first come first serve, very well known discipline FCFS. This will usually assume unless otherwise stated. If in the given problem we are not stating, then you have to assume it is a default queue discipline. Otherwise we will specify you have to use this queue discipline. If it is not mentioned there, then you have to use the FCFS. We have the discipline service in random order also. Last in first out. Last in first out means in the godown, in the stack, in the godown, right? Generally the item which we put in the last, always we have to take out first. So last in first out. FCFS first come first serve. Zero, service in random order, right? Service in random order. Where you have seen the service in random order? Any example? Hostel allocation service in random order. Maybe I do not know about the procedure of the hostel allocation. It could be. अरे आसाराम बापू जब भीड़ में माला फेंकते हैं यूं करके, जिसके भी गले में जल जाए, वो पानी ऐसा छिड़काव करते हैं जिसको भी आशीर्वाद मिल जाए, पानी की बूंद मिल जाए. डेट इज द सर्विस इन रैंडम ऑर्डर. किसी को भी मिल जाता है, वो आशीर्वाद समझ के ले लेता है. डेट इज द सर्विस इन रैंडम ऑर्डर. कोई नो पैटर्न, जिसके गले में फूल माला पड़ गई, जिसने फूल कैच कर लिया, जिसके ऊपर बूंदे पड़ गई पानी की, वो सोचता है मुझे आशीर्वाद मिल गया. That is the service in random order, right? No pattern, no discipline. Sometimes customer are chosen from the queue based on the certain priorities, such as the cost of the waiting in the line. So means sometimes we have the priority. We have to give the priority to VIP people, to emergency people, right? So it's depending over the situation. We have to decide which queue discipline. Over to all this discipline, there is one more discipline. Anyone can judge. Anyone can judge. Over all these discipline, right? Well behaved discipline, there is one more discipline. Now you can judge. Generally, we do not study that because that is the undisciplined thing. Yes. Please give the answer.
Emergency, sir. Emergency, sir.
Emergency, the priority in priority it come.
Biasness.
Personal bias. That is the correct thing. Personal bias means जिसकी लाठी उसकी भैंस, जिसमें दम हो ले जाए सर्विस यार, पहले खड़े रहो तुम जिसके पास जो खड़ा होना है। यदि तुम में दम है तो ले जाओ सर्विस, होता है ना। So that is the pictorial graph of the FIFO, first in first out. It is the LIFO, right? Last in first out. In general logistic we use. Here we have the priority. First we have to decide the priority, and priority will get the service first. Then whatever I have told you, right? Might is always right. जिसकी लाठी उसकी भैंस, जिसमें दम हो ले जाए सर्विस अपना, right? But it is the undisciplined discipline, so it is not, we cannot model, right, this type of the situation. So that is not in the list of the Q discipline or the service discipline, but it is the practical discipline. But actually in the service discipline, server decide to take the customer from the queue, but in this, customer decide you have to give the service to me at the gunpoint. So that's why it doesn't belongs to the Q discipline or the service discipline. Clear? But it is a practical situation. Now you have selected the customer from the queue whom you want to provide the service. Now we have to study about the service mechanism. Means how the what is the architecture of the service system or service facility. So that come in the service mechanism. Service station may have one server, one or more server, right? Means in the any system we may have one server or more than one server. If we are talking the more than one server, whether they are arranged in parallel or they are arranged in series. For example, in the reservation counter, you can choose any line, right? All the servers are equally important, right? They are parallel. You can take the reservation from any counter. So we have the more than one server and arranged in parallel, right? Arranged in parallel. So here we have the situation. Means we have the one waiting line. And after that we have the multiple counter. So that come under the single queue, right? That come under the single queue and multi-server system. We can have the single server, we can have the multi-server system, right? We can have the multi-queue in front of the multi-server. It means for this queue we have the single server. For this queue we have the single server. For this queue we have the single server. So we can have the any mechanism, right? We can have any mechanism. So generally in our course we will study this one. We have multiple server with single queue, and the number of the server we denote by the R, right? Or not R, we denote by the small s. Number of server we denote by the small s. How many servers are parallel? Now these servers may be homogeneous, may be heterogeneous. If these servers are machine, then it can be the homogeneous, means all are providing the service with the same rate. And if if it is not machine, they are the men. So it may be the heterogeneous, right? All have the different service capacity, right? All cannot work with the same rate, right? So here we have the different capacity. Then they are termed as a heterogeneous server. So here we have the situation of the queuing system. Now, if all the servers are busy, he will stand in the queue and will be selected for service based on the queue discipline when the server is idle. If there is a multiple server and if any server is idle at the particular point, the first customer will go to that server, right? The first customer will go to that server. Another service mechanism may consist of the several servers arranged in series. For example, in bank, you give your check to the dealing clerk, then that dealing clerk check the amount, account number, signature and all these things. Then he passed to that check to the provisionary officer. Then the provisionary officer check his signature, right? Then the provisionary officer return the check to the again clerk. After that the customer get the money. So here you are getting the service in the series channel, right? You are getting your service in the series channel. So we can have the multiple server in series also. So that type of the queue are known as the tandem queue. If all servers are busy, he will stand in the queue and will be selected for the another service mechanism may consist the several servers arranged in series. The customer receive the service from the sequence of the service facility in series. Means here we have the server 1, right? Here we have the server 2, here we have the server 3. So here the customers are waiting. So he take the service from here, then some customer are waiting here, then some customer are waiting here. So for example, in the computer system, in the RAM, we have the finite buffer, right? We have the finite buffer here. So more than that buffer capacity, you cannot accommodate the data. So you have to wait for the processing, right? When we have the different means quad 4 or right, quad 4 processing systems, then we have the 4 processor. So for the each processor, we have the finite buffer system, and here the data is coming in the series. So that data has to wait. So it means sometimes we have the situation, right? We have the situation of the blocking. Blocking means here the buffer size is full. Here if the buffer size is full, right? So this server cannot provide the service. This server cannot provide the service because he cannot send the data in the following buffer. So that is the blocking. May have the starvation, right? Starvation means he is idle, but this server is not providing the service. So at that time he has to wait for the customer. So we may have the blocking, we may have the starvation. So depending over the situation, right, we have to take the decision. We have to optimize the architecture of the system so that we can minimize the blocking and starvation. He passes from one service facility to another in a specific order. The service is complete as soon as he passes through the service facility of the series. Now, here again, each service facility can have more than one server arranged in parallel, and a customer is served by the only one server in the facility. Means it is given to you. Here we have the series 1 service system. It is the series 2 service system. It is series 3 service system. And here we have the multiple server. So we can have this type of the situation also. The elementary service mechanism assumes that there will only be a one queue for all the parallel channel in the system, right? Here whatever the system we will study in the course, in that we assume that there is one queue, right? and in front of the multiple server. There is one queue only, and the first customer will go to the ideal server. Now, service can be the single one by one, or service can be in the bulk. For example, bus system, train system, their picture system, right, movie system. There you can provide the service. You can provide the service in a bulk. For example, in the auditorium, we have the capacity of the 1,000 viewers. Then we are providing the service to all the 1,000 customers simultaneously. So that is the bulk service, right? That is the bulk service. The customer may be the customer, or server may be the person and non-person. Means sometimes we have the customer, sometimes we have the machine, sometimes we have the data, sometimes we have the call. So this data, call are not a person. So here the customer or the server may be the person or may be the non-person. Right? Sometimes we have to present physically, or sometimes we have not to present physically. For example, in the trunk call, in the booking system, we have to book, right? After the clearance of the book, means in the booking system, never we have to present physically, right? When our number turn will come, we will get the service in the token system. So queue may be of any kind. Now, when we have the queue, I have told you during in the queue, always the customer show the impatience behavior. So impatience behavior means when there is a queue, right? When there is a queue. So after before joining the queue, the customer may leave. यार बहुत बड़ी लाइन है, मैं तो आज मेरे पास तो टाइम है नहीं, मैं तो यार आज जमा नहीं कर पाऊंगा बिल. ऐसा हम सिचुएशन बहुत बार होता है ना, हम उस सिस्टम में जाने से पहले ही बाहर आ जाते हैं. That type of the behavior are known as the barking, right? That is the impatience behavior. In joining the queue, in the middle, you are seeing that यार ये कलर तो आज बहुत अच्छा काम नहीं कर रहा, इतना टाइम तो मेरे पास है नहीं. तो after joining the queue, we leave the system. That is known as the reneging. कि मतलब अब तो इतना वेट नहीं कर पाऊंगा, तो मैं थोड़ी देर वेट करने के बाद I have left the system. That is the reneging. Before joining, you are leaving the system, walking. After joining the system, if you are leaving the system, then it is the reneging. Now, if there is a parallel system, we have the two queue. ऐसा बहुत बार होता है कि यार बगल वाली लाइन तो तेज चल रही है, हम अपनी लाइन तुरंत वहां से वहां पे शिफ्ट कर लेते हैं, अपनी पोजीशन वहां दूसरी लाइन में शिफ्ट कर लेते हैं कि नहीं यार बगल वाली लाइन तेज चल रही है. तो उस केस में क्या होता है? That is the jockeying. So all these are the customer impatience behavior, right? All are customer impatience behavior. You have noticed all these things, right, in practical life. So we will study the mathematical modeling of all these things. Now you have selected the customer from the queue, you have the well-defined service mechanism. Now you will provide the service, right? So next important element is the probability distribution of the customer service time. How much time we have? Okay, so I think we will do this in the next lecture. If you feel any doubt from the today lecture, you can ask.